recording is now on, to warn everyone. Okay, well, welcome to this event tonight. This is Energy in Our Homes, so just make sure you're in the right meeting room. So our speaker tonight is Tony Duffin. Tony is a chartered mechanical engineer who's worked in the fields of renewable energy and energy efficiency for over 30 years. He has done work on behalf of the government where he has accelerated various green technologies by removing barriers and through promoting technical developments. He's also been involved in projects involving low carbon building technologies, and part of that is what he's going to talk about tonight. So over to you, Tony.
Thank you very much. And it's interesting to reflect on that introduction, and you might ask why someone who does renewable energy, why are they talking about buildings? And what I discovered in working with the various renewable technologies, including heat pumps, was that there was a need to think about how they were better integrated with the buildings. So that's what got me sort of how I got dragged into the sector, if you like, and I've enjoyed it, and I think I've made a difference. So I'm hoping to convey some of the experience in this talk tonight. First of all, I wanted to just remind ourselves of the context, and I think we all know that we have an issue with climate change, and that is in turn caused by CO2 emissions, which are increasing because of human activity on the planet, and they are throwing the atmosphere out of what was an equilibrium position, absorbing enough heat from the sun to maintain a nice temperature, just a comfortable temperature for life. But this is a quote from a speech about the impact or potential impact of climate change, and I'll just read it out here. The result is that change in future is likely to be more fundamental and more widespread than anything we have known hitherto. Change to the sea around us, change to the atmosphere above, leading in turn to change in the world's climate, which could alter the way we live in the most fundamental way of all. And you might think that you could imagine Sir David Attenborough giving that as a speech at the recent COP26 last October. But this was given by Margaret Thatcher in 1987. It's to me, I still find it staggering that long ago we knew this was an issue, and we're still really grappling with how to change how we handle energy and CO2 to reduce our emissions and deal with this problem. So that's the context of it, and therefore a lot of what I say is about reducing energy because we want to reduce CO2 emissions. This is how I've structured the talk. I want to start by talking about how much energy our houses use, to talk about some averages, and then a little bit about how we can look at how they use energy and what is important, and how we can understand how to improve things. The second part is about how, as it says, the construction and insulation influences this, and I want to talk about some concepts which are used in the construction industry and lead us through to ways that we can use knowledge and understanding of insulation and heat flows to improve buildings. And then finally, what does that mean for the decarbonisation of heating? And one of the threads that I will have running through all this is that I'm interested to see how we could, for example, use new technologies, lower carbon technologies, such as heat pumps, to heat our homes, because they're not an immediate switch over from gas boilers. So how much energy do our houses use? Now, I've blanked out the middle of this chart. These are Ofgem figures, and I just want to explain the table, I should say, before the numbers. So across the top, you'll see we've got these various columns. There's gas, electricity, then there's electricity if economy 7, and Ofgem take all the data they get from a huge number of energy meters, and they have sliced it up so you've got low, medium and high users. You'll see the column on the left there splitting it up. The reason they've split out economy 7 is that if you have economy 7, generally speaking, you're either actually heating your home with economy 7, even though potentially you might have gas for cooking, but you may be using economy 7 for heating your hot water as opposed to a gas boiler. So there are, in some respects, there are some quite confusing numbers and crossovers in this chart, but there's a key conclusion that will come out of it. Also, one other point I want to make at the far right there, the approximate annual bill, you'll see the low is 700, the medium 800 and the high 1400. These are Ofgem figures from early last year. So we've all spotted, I'm sure, that these numbers are going to be going up quite rapidly if it hasn't already affected you. And I'm hearing of certainly between 60 and 100% increases in these numbers. But these are the numbers from the Ofgem data that I was using at the time I put this together. So let's move away from the costs and look at some kilowatt hours per year. So here we can see for gas, low user 8,000, medium user 12,000, and a high user 17,000 kilowatt hours a year. I know that high is a sort of an average of high users. There are houses that use a lot more than that. Then if we look at electricity, we've got low, medium, high, 1,800, 1,900, 4,300. And then with economy 7, you'll see that, unsurprisingly, there's an increased amount of electricity if you use economy 7. Two things I want to say about this is, one is that the gas kilowatt hour use is considerably more than the electricity use. And in the context of the current electricity supply and the generation mix we have in the UK, gas is also by far the more significant source of CO2. Because what has actually happened in my career in this sector is that the electricity generation mix has massively reduced the amount of CO2 emitted from electricity generation. So what that says is that if we're looking in the context of energy use and carbon, then it's about the gas use. So let's have another look at how much energy our houses use. So this is a plot, as you can see, by month for 2020, and then the vertical axis there, we've got the kilowatt hours per month, and the blue line is electricity, the red line is gas. And we immediately see two key seasonal trends. Well, with electricity, of course, there isn't much of a seasonal trend, and the reason for that is that, you know, the slight dip in the summer, we don't use so much electric light, and we don't use the pumps and fans on our heating system, so a slight dip in the summer. Gas use, meanwhile, for heating shows, unsurprisingly, a significant increase in the winter. But this alone doesn't necessarily help us. And here are some questions we might ask immediately. Why is it so high a gas use in December 2020 compared to, say, January and other months? You know, there are odd shapes going on there. So what is going on? And on the blue line, then, yeah, why have we got these wobbles? Now, I'll admit that this is actually for my house. The wobbles on the electricity are because we bought an electric car. So immediately we can see that owning an electric car makes a very significant difference to your electricity consumption, and that's unsurprising. It's almost doubled it in December. Of course, that has meant we don't buy petrol and diesel anymore for that vehicle. So from a carbon point of view, we are switching energy sources and reducing carbon that way. But the gas use, so what else can we do to understand why we've got a high use in December? There's a technique called degree days. So here's a chart showing how we can understand what's going on. And this is trying to show how gas consumption in a month varies with the coldness of that month. And degree days is the term used to describe that coldness. I'll explain how we get to degree days. You can use them for what you might call hotness if you're looking at air conditioning units. But the plot we get when we look at this coldness measure, this degree days, so that's along the horizontal axis, and now we've plotted the kilowatt hours in a month up the vertical axis, and we get what is here a very characteristic shape. It's more or less a straight line. There's a little bit of scatter, but it's more or less a straight line, showing that the colder it gets, the more gas is being used. And what that would say to us, thinking about the last chart, is that that December must have been substantially colder than the January, and hence the heating system used more. There's another characteristic to this chart. You'll see, I don't know how well my cursor shows up, but down at the bottom here, probably around 70, 80, there's a knee in the line, and that is because around that point where we've got degree days of around 80 in a month, this particular house doesn't need heating, and the gas use to the left of that point is to do with producing hot water. So that hopefully will become more clear if I talk about what a degree day is. So this is how you calculate them, is the best way to explain it, I think. So step one, you choose a reference outside temperature. So what is outside your house, and typically we use a IMechE station number rather than necessarily recording the value directly outside the house. And the reference temperature is essentially the equilibrium temperature at which you don't need to heat the property. And for the UK, that's typically taken as 15.5 degrees centigrade. So you take that reference, and then for every hour, you calculate the delta between that reference and the actual temperature. So, for example, if you're looking at heating degree days and it was 13.5 degrees outside, compared to your reference, you've now got 2. It being colder, so you record that 2, and then you go through all the hours in that period you're looking at, and you add up those degrees. And then, of course, what you've got immediately is degree hours, but you then, with the relevant maths, simply dividing by hours or days, you can produce degree days for the day, the week, the month, or the year. Now, that 15.5 degrees centigrade number it's a good starting point as a reference, but actually it will probably vary according to how well insulated the house is, because if you insulate a house very well, it is isolated from the outside, and therefore it is likely to stay warmer by itself. We have in all our houses what are called incidental heat gains from, for example, when you boil the kettle, or from when you're watching the telly, or your lights are on. Even though they're low energy, there will still be a certain amount of heat going into the building. Even people and pets will produce a certain amount of heat. And if you think back to the amount of electricity that was being consumed, so around 2,000 kilowatt hours for a medium user, those kilowatt hours are generally speaking all going to go into the house, unless, for example, you have a pottery kiln at the bottom of the garden. That electricity will turn up as heat inside the house. So you've already got a bit of heat coming in from those sources. So a well-insulated house will tend to require a lower equilibrium temperature than a poor house. Still, this broad knee shape in a straight line curve is what we're looking for. I just want to show you what we might see in some other data. As we can see here, there's an awful lot of scatter. I've deliberately chosen this chart, and I'll admit to something in a minute about it. But this is typical of what you can see in real data for real buildings, and this is real data for a real building. And it appears that we've got 3 trends as well as the scatter. So an immediate conclusion might be that the heating is not responding properly to the outside temperatures. Especially if we look at the upper line here, there's a lot of scatter there. We might quite reasonably say, well, why would we use this much heat here compared to this much heat here, when the degree days were hardly any different? And then we have another trend here, apparently, and we have a third trend right down here on the 0 line. Now we do see trends like this, particularly in office buildings, but you could see it in a home. So, for example, this trend could be when the building is occupied. This could be because the building is just on a frost setting, and this could be because the heating is completely off. So seeing this sort of scatter on a chart is quite useful compared to the previous chart. Now, the admission I'm going to make is this is actually for an office building, and to be fair, this was before the data was cleaned up. And what we actually discovered in looking in detail at the data was that down here, this was automatic meter reading data. Actually, we had dropout rather than zeros. And similarly, for some of this data, we had dropout rather than zeros. And the other admission I have to make is we have here degree days for individual days rather than months. So if we clean this up and then replot it, we have a much nicer looking chart, a nice straight line. But if you remember, I pointed out for the house, the knee in the curve was over here somewhere. For this building, it's right over here. And what that says to me is that either this building is much less well insulated, so it requires more heat for the given coldness, if you like, or it's being overheated. And it is quite possible for an office building that is what is happening, because to be frank, no one's really in charge of what the heating's doing in office buildings, is my experience. It all gets lost in the noise. So that's a look at consumption versus coldness to help us analyze what's really going on. And another way of looking at it is to think about where do those losses go and what do they cost us. So this image on the left gives you a broad indication for a typical house of how much energy goes through different bits of the fabric. So the biggest number to the left there, 35%, is it indicates that all the walls, not just this gable end, but all the walls, all the basic structure with that, but not the windows and doors. The roof is about 25% up here. Windows, glazing generally, and any glazed doors, about 10%. Drafts is another one, about 15%, and then the floor also about 15%. Now, some caveats on this. It does depend on the building, but if this was about buildings as they were built and unmodified, then broadly speaking, this is going to be the same. So a Victorian building with a solid wall, limited insulation in the roof, single glazed sash windows, probably this is about the right split. And if you compare that to, say, a 1980s building, which had cavity wall insulation, plenty of loft insulation, and double glazing and draft strips, again, probably the proportions are about right, but the totals are going to vary a lot. And then as a crude rule of thumb for the average house, based on those old Ofgem numbers, this is telling us roughly how much money is going out through those bits of the fabric. And I won't read the numbers out there, but what I will say is that, of course, that says that if you can cheaply insulate your roof, and that is the most cost-effective part of a building to improve, that is where you're going to save money most quickly. And typically, I would say that a roof these days should have about 350 to 400 millimeters of rock wool or an equivalent in it, and then you'll knock that £200 down to probably about 50. In contrast, double glazing, which is something which tends to be focused on a lot, you'll see the heat loss is relatively small as a proportion, and the cost on the Ofgem numbers was about 80, even doubled to 160. That still doesn't sound like it's going to be cost effective. So there tend to be other reasons for thinking about why we might do double glazing, and those are partly because they do impact on drafts, and partly because every now and then, of course, we find that if it's existing double glazing, the glazing blows, it's lost its effect, it's got condensation in it, we want to change it anyway. Or if you've got wooden frames, they start to rot, and indeed that's certainly that happened to me a few years ago. Despite them being hardwood frames, properly treated, they started to rot, so they needed to be replaced. And of course, the other conclusion here is the walls are a very substantial route for heat loss, the most expensive part, but of course it potentially is the most expensive part to treat as well. And in my view, that is why we should make sure buildings are built properly from day one. So that was how much energy these houses use, and some idea of how we might analyze it and the costs. So what I now want to talk about is a bit more detail on how construction and the insulation will influence those numbers. So to start with, I'm going to introduce this concept of U values, and many of you may know about this anyway, so apologies if this is not new to you, but it's the construction industry's shorthand for conduction. The units are watts per square meter per degree C. So what that is saying is, a degree of heating power is being lost through an element of the building for every square meter and for every delta T of a centigrade. So it is actually a very good unit when you are designing a building to help thermal modeling and to understand how the structure could be improved. There are some shortcuts taken in it. So the U values that you get for a piece of a building are averages, regardless of, for example, wind speed. Anyone who's worked on heat transfer as a mechanical engineer, you'll know that forced convection, so air moving at speed across a surface, removes much more heat than natural convection. And that must apply to buildings as well. So if it's a windy day, the U value must change. It must lose more heat than on a still day when it's just convective loss. Similarly, if a brick wall is damp, we will need to evaporate some of that water off, and that will clearly take away more heat. Whereas if you've got a non-porous surface like just a glass window, then that's not going to evaporate water in the same way. And there are also some fine details of the construction which are not fully taken into account in calculating that average U value. But where it is useful, and the reason I think it's evolved to the extent that it has, is because when you're trying to describe quite a complex sort of sandwich that you might have in a wall, which might start, for example, on the inside, you might have a plasterboard layer, then an air gap, then you've got a block which in itself is partly insulating, and it also has mortar between the joints. Then you've got, you might have a partially insulated cavity with a certain type of insulation, and then there might be an air gap, and then you might have brick on the outside, so that would be one sandwich. Actually, the simplest way to handle this in what is a relatively unsophisticated industry is to have a U value that describes that wall. So what sort of values do we get? This table is showing you, so each row is an element of the building, and you'll see on the left there, so I've got the wall, the floor, the roof, and a window. And then I've got you here a column which is the lower performance type of structure with its U value, and then a higher performance one and its U value on the right. So if we work our way down the rows, so a 4-inch brick wall, that's 4-inch thick, so that's one brick thick, and that might be something you would find in a Victorian building, the scullery, for example. A few houses just have 4-inch brick wall. It might be that someone's converted the scullery into a utility room, and that's the thickness of the wall. So that U value is about 3 watts per meter square per centigrade. A higher performance, right at the top end, passive house, which I'll talk about a bit later. So that's a really top end building, very high levels of insulation, very low energy use. So there we can get to 0.09, so very substantial change. Let's see, 1/30th or better. Then the floor, so the sort of worst case I would expect to see would be a suspended timber floor over a ventilated void, and typically again that might be Victorian, but we do see those even in houses up to about the 1960s, and there we're losing 1.5 watts per square meter centigrade. But a modern floor, which would typically be solid, but it can be a modern variation on suspended, which we call beam and block, you have insulation both around the perimeter and underneath it, and there your U value is 0.1, so again very substantially lower. A roof, worst case here would be a flat felted roof with no insulation, just the roof joists separating the felt from the plasterboard inside, and there you've got about 1.7. And again, a modern loft with 450 mil of rock wool, very substantially lower, 0.09. Steel frame, single glazed windows, about the worst with 5, and then your best coated triple glazing about 0.08. There are people claiming about 0.6, but I would say 0.8 is more realistic. The next question then is how might that build up to how a building is actually losing heat? Oh, sorry, before I do that, I've got one more element of heat loss, which I nearly forgot. Ventilation. When cold air comes into a house, it must push warm air out, and of course we have to reheat that fresh air. So we have to consider those air changes, and the reason we have them is because inside a house you have sources of moisture, whether it's just breathing or showers or boiling that kettle or whatever. We also have some pollutants from cooking. There are plastics in our house. If you have a new carpet, there's that new carpet smell, which is actually VOCs, and of course we have CO2 from people. If you didn't ventilate that, then the air quality inside the house would become unacceptable. So as an indication, 1 air change per hour is about what we need to maintain a healthy environment. Slight caveat again, it will depend on how many people are in the building, what is going on, and how big a volume of air there is in a building, but that's a good indication. So as I say, we need to heat the air to maintain comfort. And as an indication, if we had a 10 meter by 7.5 meter floor plan on a building and two stories, so 4.8 meters tall, that volume with a delta T of 15 centigrade, so 5 degrees centigrade air coming in, but we wanted a 20, you need about 1.5 kilowatts continuously to keep that air up to temperature. So now I'll build that up into a typical house. And here we're building it up to similar looking to the U value, but it's watts per centigrade, because now we've multiplied up by area. So this is telling us the sort of specific heat loss for a building. I've used that 75 square meter floor plan as an example, and this is considered the sort of nominal small average house in the UK. So the fabric conduction losses, so we take all those U values, the U values of the windows, the walls, the floor, and so on. For each element, we multiply by the area, and then we get the totaled up watts per centigrade. For the air changes, we take the volume and the specific heat of air and the flow rate and so on, and then we get another number. Coincidentally, these are very similar. And then we top them up. Total specific heat loss for this building is 116 or so watts per centigrade. And now you can see for 2 different delta T's, so one at 12 degrees centigrade, so if it was 6 degrees outside and 18 inside, we have 1.4 kilowatts required to keep the house comfortable at that 18. And if the delta T is 23 centigrade, so now we've got a frosty day outside and someone wants it at 22 inside, then we need 2.7 kilowatts. To me, 2 things jump out straight away. One is that, of course, delta T is important, which is why, and hopefully this is no surprise, if you set your thermostat down a bit, you will save energy because you're reducing your delta T. I was listening to something on Radio 4 the other day where they thought that someone had said the average temperature inside people's houses was 24. I don't believe that, but I do know people who have their house at 22. I don't. I'd rather wear a jumper. So that's the modern, well-built house and a relatively small area. If we go up now to a sort of an exemplar Victorian house, we might call it an old rectory. Here it is. It's got 300 square meters of floor area, so 4 times the size of that other nominal house. Here we're using the older types of fabric. It won't be a 4-inch thick brick wall. It's probably 9 inches, but it won't have insulation in the roof. Certainly won't have any under that suspended timber floor, and it's probably very draughty. It will have fireplaces. It will have rattly sash windows. The suspended timber floor has probably got gaps in it because the timber's dried out over the century or so it's been there. So we have higher air changes as well. Total specific heat loss is more than 10 times what we saw in the small building. And you can see now for those 2 delta T's, 19.5 kilowatts and 37.3. So that building is at the limit of what you could fit a single domestic gas boiler in to keep it warm. Quite a substantial difference in heat loss. And it's a combination of the size and the older fabric. Now, there's another way of looking at the sort of specific heat loss. So I'm now going to look at how those older fabrics, building fabrics and older U values have changed and have improved and are going to improve in future. This is another industry convention where we're looking at watts per meter square of floor area. As an engineer, it makes me wince, but this is what the construction industry uses. The particular problem with this is that per square meter of floor area doesn't differentiate between, say, a bungalow and a 2-story or even a 3-story building, when the surface area to volume ratio will change dramatically. But it is used as a comparison. There's a certain amount of benefit in using it. So this table here shows essentially from left to right how buildings have improved over the decades. So the Victorian uninsulated building, the old rectory that I used, if you like, in the previous example, watts per square meter of floor area about 150. By the 1980s, just by having cavity walls, a little bit of loft insulation, and not having suspended timber floors, we've dropped it to about 100. The current regulations, which of course require insulation in the cavity and a very substantial amount in the loft, and double glazing and insulation under the floor, we've now dropped it to 50. And the next step, the blue between the pink and the green there, 40, is what the new regulations, which were announced recently, they are about to come into force this June. That's what they're aiming for in energy terms. And finally, the green passive house, so 20 watts per square meter. Now, I put some notes at the bottom. I just want to pick up on those. So, as an indication, if you've got a building with 50 watts per square meter of floor area, then that's the peak heat demand, I should say, as well. You are talking about roughly 75 kilowatt hours per square meter of floor area of annual energy. So that helps you understand a bit about how the bill will build up from that number. But as I say, it depends to some extent on the geometry of the building. And then another point on the new regulations, the energy use has not dropped very much, but the new regulations are requiring a 31% reduction in CO2 emissions. And the way the regulations are framed means that whoever is designing the house and then building it, they have the choice as to whether they add even more insulation or whether they use a low carbon heating system. And that is the idea behind these new regulations. It allows a bit of selection by whoever's building it, and that might potentially be because of where it is. If it's off the gas main and it's straightforward, you'd fit a heat pump. If you're on the gas main, you might not want to fit a heat pump, but you do have to put more insulation in. The passive house, very low energy consumption. The sort of indicative aim is that they don't have a dedicated heating system, or they don't have to. These are already being built by, for example, social landlords and many self-builders as well, where you have an ultra high efficiency home. So it's not pie in the sky by any means. So let's talk a little bit more about what are passive houses. I've got some photographs here, and then the bullets about what the specifics are. So first of all, they do have very high levels of insulation, and that simply means very thick insulation. And on the bottom photograph, I don't know how easily you can see on your screens, but it's just visible here how deep the reveal there, where the window is fitted is. And I know this particular house had 300 millimeters of a foam insulation on the outside of a heavy concrete structure. The other thing that is done to passive houses is they are very airtight. And what that means is you have to have active ventilation, and that active ventilation will have a heat recovery system in it, so that as the warm air in winter is blown out to maintain freshness of the air inside, you bring in cool air, you pass it through a heat exchanger, and you swap as much of the heat as you can. And a good unit, well installed and operating at its correct settings, should achieve over 90% of heat recovery in an active ventilation system. The other thing you should have in a passive house, excuse me, is good thermal mass. I mentioned the one at the bottom has a concrete structure as its internal surfaces. And the point about that good thermal mass is that it modulates and moderates temperature changes. The summer heat, for example, as the temperature outside rises, the house will gently absorb that heat. It won't suffer from overheating on a really hot day. The thermal mass will slowly absorb that heat. So over the period of a number of months, it might rise from, say, a nominal 18 to a nominal 20 degrees centigrade. And then in the winter, of course, the reverse happens. Some of that warmth locked up in that fabric will slowly be re-emitted into the building, and it will gradually cool down, but it won't feel uncomfortable. We won't get those swings of temperature. And if I can use what I hope is an example people understand, it's a bit like the difference between, say, walking into the cricket pavilion in the village, which is a wooden structure, has no thermal mass. In the height of the summer, it immediately gets incredibly hot. Compare that to walking into a cathedral, where even on the hottest day, all that stone moderates the temperature right down, and it will always feel cool. And then the final point is that passive house buildings have optimized insulation and fenestration. And I know that's an awful lot of syllables for just windows, but insulation is actually the science of managing how the sun's rays and the sun's heat enter the building, and that's by time of day, by time of year. So you arrange the glazing in a certain way around the whole building. And then, of course, fenestration. It's about daylight as much as anything else, and how you ensure that you can use the building without electric light. And the tendency is that we see buildings looking much like this one, where we have, as we can see, large glazed areas. This is on the south. There's an overhang over the top of the windows, and I know this one also had a canopy which would extend. And the idea of that is that in the summer, when the sun is high and the sun is hot, it prevents the sun's rays getting inside the building, whereas in the winter, when the sun is at a low angle, it allows the sun's warmth, what there is of it, into the depth of the building. I would comment that we can see these are roof lights. I suggested they shouldn't be there because this is doing exactly the opposite. Here we have, and you can imagine in the summer, the sun burning through that roof light into the room below. The client and the architect didn't want to change it, so I reckon there's a risk of overheating in those two buildings. The other photograph, this building is a passive house. This is the original architecture on this housing estate. This is in Totnes. The owners of the building on the left decided that they wanted to upgrade and tidy up their building, and you can potentially see why, because of the colour of the render on that one. Something had gone horribly wrong with the render. So they decided while they were doing all that, they would add external wall insulation, they would improve the air tightness. I think they extended at the same time, added triple glazing, and added mechanical ventilation with heat recovery. And this is the conversion. This is the result of that conversion. And it's actually a few years ago, anyway, it was a bed and breakfast in Totnes, and I've actually stayed there. And yeah, fascinating, interesting building, very comfortable. Yeah, it can be done. We don't have to start brand new. We can convert. Now, I managed to accidentally pop this little title up, example standards. So I'm going to list a couple of standards, but the point I wanted to make about this is that these standards have been around for a while, and if any of you have been involved in the development of technical standards, you'll know it takes a very long time. So the fact that they exist and that they are in use implies, and indeed it's true, passive houses have been built and are in operation around the world, and they have been so for quite a while. So in the UK, we had something called Code for Sustainable Homes. You can still get the document online. It wasn't specifically about passive house, it was about broad sustainability issues. But a level 6, which is the top, was zero carbon. And to achieve zero carbon, most houses would essentially become passive house levels. The name passive house it's been borrowed, unsurprisingly, from German. But in Germany in 1988, they were building and experimenting with very low energy houses and what are now called passive houses with less than 120 kilowatt hours per square meter per year. Their standards have improved since then, but that's how long it's been around. And we also have something called Super E in Canada that's been around for at least 7 years, and something called IMechE in Switzerland. So it's a technique which is well tried and tested. So we looked at how much energy existing buildings use. We've looked at how we might change that by improving insulation. So the question I want to now talk about is, what does this mean for decarbonising heating? So let's look at what we currently use for heating, which is the red one, gas boiler. Yeah, why would we use it? Here's the pros in the next column. Well, obviously, very high temperature output, which does two things for you. It means you can have quite small radiators, and it means you have a very fast warm-up. Suits conventional designs of houses. It suits a lot of modern living for people who may not be in the house during the day, and it's convenient. We're used to it. The other point, of course, is that the gas invisibly and magically just comes through a pipe into our houses, and we don't have to think about where the fuel is coming from. It just exists. Then there's biomass. Similarly has high temperature output, which also means you can have small radiators and a fast warm-up. It is CO2 neutral if the fuel is sourced in the right way, so we've got a definite step change in how we might heat buildings. Then we have heat pumps. These are extremely efficient. For about a kilowatt of input, you will typically get 3 to 4 kilowatts of heat output. And this is why there is so much interest in them. And indeed, there has been so much interest in them for many years in other countries. An air source heat pump will typically give you the 3 kilowatts out for 1 kilowatt in, and a ground source heat pump will give you 4 kilowatts out for a kilowatt in. There are some very robust and reliable designs out there. And of course, if we're using renewable or certainly low carbon electricity, then we get an extra boost of extremely low carbon heat, because the heat source for the pumps is the natural warmth around us. So an air source heat pump extracts it from the atmosphere. A ground source heat pump, as it says, extracts it from the ground. And then I've added in brackets a mechanical ventilation with heat recovery, because I think it's not directly a heating system, but it's part of the whole package. If you are going for decarbonised heating systems, then it's an active device. It's not just dumb insulation, it's an active device which could be part of your integrated plant. And there are one or two systems where the mechanical ventilation with heat recovery system actually has the heat pump integrated. If you're down at very low energy uses, very low powers, then that's a system which works very well. So what are the disadvantages? Well, gas boiler, CO2 emissions, and of course UK sourced natural gas is declining, and that is partly why we are exposed to this ridiculous spike in gas prices at the moment. We are no longer a net exporter of gas. Biomass, well, the two problems really with this. One is the lack of scale of the fuel resources in the UK. We just don't have enough waste wood and other materials that could be used. And then the other big issue is transport. That it would be, I think it would be unthinkable actually to try to supply some of London using biomass, because the amount of fuel you'd have to transport is colossal. Indeed, it's quite an eye-opener. Some of the clients I've worked for who are building new low-carbon houses or retrofitting biomass to their houses where they've had oil before, it's an eye-opener to understand just what volume of biomass you need, especially if you've converted from gas, where you didn't have to think about where the fuel was coming from, and suddenly you've now got, say, 4 cubic meters of storage, and that isn't your whole fuel consumption for the year. So the transport of that would be quite difficult. So difficulty with heat pumps then moving down. They are electrically powered. Well, that in itself isn't a difficulty, but in the UK, that means we will need much more electricity generation. to flip from using gas for heating to heat pumps for heating. And also, if we don't get this right, we might need grid reinforcement because the power rating of some heat pumps will be so high that it might just put too much demand on the grid. If you think back to the Victorian rectory that I talked about, where it had 30 kilowatts, 37 kilowatts, I think, of gas boiler requirement. Well, even if a ground source heat pump was used on a 4-to-1, we're still going to need nearly 10 kilowatts of electricity running continuously to heat that rectory. I wouldn't actually recommend doing that, but that's the sort of scale of the issue that we might have. And typically houses have a peak capability, that is a fused rating of 24 kilowatts. So we're suddenly potentially adding half again to the rating or the draw that might appear from that house. Disadvantage with mechanical ventilation with heat recovery: you need a very low energy and a very airtight house, and retrofitting for airtightness is quite a complicated and tricky process. You need to get below a certain threshold before it makes sense. Great in new build. And some comments. Well, the gas boiler is, of course, the most common in the UK. And if we are serious about decarbonising the heating system of all UK homes, we're going to need to either replace them or use a different fuel. And of course, there's talk of hydrogen. I'm not going to talk about hydrogen in this presentation. Biomass, well, there is actually a very good match to large farm or forestry estates and remote rural homes. So there's an opportunity there, especially if we've got, again, let's talk about the Victorian rectory. If that's out in the middle of the countryside and is near to a farm estate and forestry and so on, then actually biomass might work very well there. And I have actually worked on a system, a district heating system for a farm estate where I think there were 4 dwellings and some other office buildings and so on. The farm estate had natural, original, woodland and some managed planting specifically for wood. It's an excellent match to the operation of that farm estate. They've got the labour, they've got the storage facilities, and they had the building in which they could put a large biomass boiler. So it worked very well in that circumstance. Heat pumps, then, the comment, well, they will be viable alongside energy efficiency improvements, and I'll talk a bit more about that a bit later. And then, yeah, MVHR, mechanical ventilation with heat recovery, is at the core of passive house. So if we aim for that in new build, then it's a straightforward inclusion. Heat pumps, where do they fit, and where might these other technologies work? I'll try to explain. This is where it does get quite complicated. So here I'm trying to compare the kilowatt peak heat requirement of homes and to see whether they might be what I'm calling heat pump ready. So this chart tries to illustrate how the peak heating demand, and that's essentially the rating of your heating system, how that varies depending on the size and the insulation levels of the building. So down the bottom here, this is the insulation quality, if you like, of a building. This level is the uninsulated, the old Victorian rectory again, that's getting in for such a bad press at the moment. And at this side we've got the passive house level, and in between we've got the different sort of stages of improvement in building regulations. And then as we go upward, we'll see these lines are telling us where the sort of threshold of the floor areas are. So this is your sort of middling small house. Here's a bigger property, and there again is our, as far as I'm saying, a much maligned Victorian rectory. And what we have in here, these 3 bands, is different, if you like, sort of qualities of the amount of heat. So down here in our small and either very small or certainly passive house insulated levels, we have no heating required. So this, even here, even older buildings, if it's an older apartment, it might be small enough that you could just retrofit a heat pump. Here, in the sort of, what's that, about 5 or 6 up to about 30 kilowatts, yeah, you could fit heat pumps here. I wouldn't recommend fitting directly a 30 kilowatt heat pump if you had a 30 kilowatt boiler. I think energy efficiency measures would be better, but it is not infeasible. And I'll talk a bit more about what those energy efficiency measures might do to that number. But once you get up here, I think this is really impractical. The numbers of buildings we'd have to retrofit would put that extra load on our grid that need reinforcing, and we would certainly need an enormous amount of extra electricity generation. So this is where we have to think of something else, either that biomass solution or yeah, maybe we have to refuel our gas. Maybe hydrogen is the answer up there. So what are the implications for new build houses if we're looking at heat pumps? And I think they are an opportunity for heat pumps. So first of all, very simply, U value should be much better. The air tightness should be much better, and then we fit mechanical ventilation with heat recovery. There are techniques for testing buildings as they're constructed to make sure that they are made airtight, and there are levels which can be certified at which there's no problem with a mechanical ventilation with heat recovery. I would say we need to go ultra low energy, such as passive house, and I've already said there are some, certainly self-builders, but also some registered social landlords are building at passive house level. So it's not impossible by any means, and it's proving practical if social landlords are doing it. The flip side is that at this point here, it's difficult to use traditional brick and block to get to such low energy levels and such good air tightness that you can realistically think of a heat pump. It's partly because of the way the construction industry operates, but it's also partly because of the constraints on it. You're working in a field in all weathers. The work is done under time pressure. Quality is only really seen at the very final finishes with the paintwork and the final plaster levels. So to be frank, there's a lot of corners cut in brick and block. In addition to that, if you want sufficient insulation in the thickness of the wall, and if you remember the passive house in the photograph had about 300 millimeters of insulation. If you're trying to fit that in a cavity between bricks and blocks, your wall becomes as thick as a castle wall. You've lost a lot of area in just the wall structure. So you need other techniques, and this is where we come onto this list at the bottom. Timber frame. There are some very good quality timber frame companies around. It's what's used commonly in the United States and Canada. There's lots of thickness in the wall for insulation. The next one is structural insulated panels, or SIPs. This is basically a technique where you create a sandwich structure, largely of timber, but with injected foam in the structure. And they are typically made in a factory, and you end up with a kit of parts brought to site. There's another technique called insulated concrete formwork, or ICF. Here you build a sort of hollow Lego brick structure. Typically it's polystyrene, to put the shape of the house together, and then the hollow spaces are then filled with bits of reinforced concrete. So you end up with a reinforced concrete structure and lots of insulation wrapped around it to give you your high thermal performance. Timber frame and structural insulated panels are probably going to be increasing the off-site construction, and the advantages are exactly the opposite of the problems for conventional brick and block, which is that you can work in a factory environment. You can build kits of parts to be put on lorries. They can be built to high quality. You've got potentially 24-hour working. You've got lots of lighting to see what you're doing. It becomes a production line, so it's fast. You can manage your waste very well. You can use computer-aided manufacturing and so on and so on. And we're beginning to see a shift to off-site construction in some sectors already. The passive houses that registered social landlords are using are typically off-site construction. Some of them to the extent that they even build the whole of the ground floor, and that's in the factory, brought in on the lorry. It's already got the electrical wiring fitted and the plumbing. It's connected together as you build the second floor on top of it and so on. So quite substantial changes occurring there. What about existing homes? There are some specifics that we would need to do. One of them, which is often overlooked, is you'd need to install an appropriate hot water tank if you're going for the heat pump solution. And the reason for that is that a heat pump produces output at a lower temperature, and indeed maybe they should be called warmth pumps. Typically the output will be about 45 centigrade, 40 to 45, and that's because of the thermodynamic cycle they're using. They retain their high efficiency by keeping the output low. What that means is you need a different heat exchanger in the tank compared to a gas boiler. It also means you need a much bigger tank, because if you can think of how you might have a shower now, certainly from a combi boiler, you get hot water, you dilute it with cold to get the right temperature. If you've got a classic immersion tank, again, the water can be very hot. You can dilute it with cold, but not use very much of the hot tank. When your tank is only 45 centigrade, you're going to use a much larger volume of that water. So you need a bigger tank. I don't often hear that being mentioned when we talk about heat pumps as a retrofit for existing buildings. And I think it's an area which will actually cause some confusion, and also potentially it's a barrier, because where people have a combi boiler in their houses, they don't have a hot water tank. So where are they going to put it? The other thing, of course, we need to do, I think you'll guess this one, is we need to insulate. It's simple in some cases. The roof is an easy one to do, but wall insulation and floor insulation might be more difficult. But there are techniques, and there are companies offering, say, external wall insulation. And bottom right here, this isn't a photograph of a vet giving bad news to a farmer about a sheep, although it could be mistaken, I think. It's showing some loft insulation being rolled out into an older building. And then we need to make the buildings airtight. Now, this other photograph that's with a lot of red in it, this is showing the beginnings of an air pressure test in a building. So we've got the big white circular thing here. This is actually a cap in a fan unit. The red here is a flexible but impervious structure which you put into a doorway. And then at this stage, this young lady is setting up the laptop, is doing the initial calibration test, checking the temperatures inside and out, checking the pressures inside and out, checking it's not that the existing wind levels in the day aren't causing too many fluctuations. The next stage is very simply take the cover off the fan, and then you set the fan to a known speed, which you can vary, set a pressure difference across it, and then you know what the flow is and what the pressure difference is across the fan. You can then certify the air tightness of that building. And also at the same time, you can have someone look around the building to find out where the air leaks are and seal them. And it's a very effective test in a new build, typically done twice during the construction, each time taking maybe a couple of hours, go around, find the holes, seal them up, and then return later when the next stage of construction is done. And we can get some very airtight buildings like that. And I would say for existing buildings, we should aim for roughly halving the peak heat load. I think that's a practical level to go for if you use all these various techniques. Now, I spend quite a lot of my time talking to ordinary people, non-technical people who don't have a particular carbon target in mind, and working at the moment, in fact, for a community group in North Oxford. And something that also we should not overlook is the barriers to change. I've talked so far very much about the dry technical stuff and what can be done, but let's look at some of these barriers. This one, and I'd written this quite a while before the big increases of gas prices we've seen. Well, yeah, high fuel bills, no spare capital. People are suffering cost of living increases. Where are they going to get the money from to do all this work? The average time in a house is typically 7 years still, so the paybacks need to be less than that, but they're perceived as longer. They're not necessarily longer, but they're perceived as longer. And I think if you look at the current massive increases in energy prices, actually, if you'd done some energy efficiency work a couple of years ago, you'd be laughing, because your payback would just have been reduced by about 3 or 4 years. But they are perceived as longer. And actually, people perceive that their time in the house will be less than 7 years, and that's not always the case either, but it's a barrier. There's a perceived lack of credible suppliers and installers, and in fact, I think there are some incredible suppliers and installers, And every now and then we get problems like Grenfell Tower, where that dreadful disaster caused by lack of quality control in the whole process, in my view. How can you put such flammable insulating material outside a building? That has influenced the way people look at external wall insulations. There are, to be frank, deliberately mixed messages in the media from the energy industry. Why would British Gas want you to buy less gas, I ask myself, by insulating your house? Busy family life, people don't have time to think about it. It's quite complex to go through the process of finding a company to do the work. What is the work you want done? How much is it going to cost? Is it going to pay back? And so on and so on. People just don't have the time to think about it. Risk, suspicion, and doubt generally. Inconsistent government policy, and there are many disincentives is another one. We've had the Green Deal, which was cut about 8 years ago. It was replaced briefly by another home insulation process, which turned out to be too complicated, run by a call center based in America, and has just collapsed into nothing. We don't have a replacement. We used to have a feed-in tariff on solar PV. We used to have a renewable heat incentive on heat pumps. They've gone. These things come and go all the time, so it's very difficult for people to believe that there's going to be ongoing support. And then there are disincentives. For example, a new build property doesn't require VAT to be paid on it, but if you're improving your home, you have to pay a lot of VAT on the materials that you're using and the work that's being done, unless you want to go through an incredibly complicated bureaucratic process. So yes, another disincentive. And then there's just general peer pressure that there's the sense, I think, that a lot of people would rather have a nice new car or a brand new kitchen because they feel that that's what their friends and neighbours, and that's what Facebook would be telling them they should be doing. Still, if we do get there, what are the implications of fitting heat pumps to many homes in the UK for electricity supply? And this is a quick calculation. So if I estimated the broad UK potential, and I said at roughly half of our homes, and let's say that's 13 million dwellings, and I forget exactly what heat pump number, it's about 10 or 12 kilowatts, I think. So we've reduced the heat demand of these homes. We've fitted, therefore, a reasonably small heat pump with only a few kilowatts of heat demand. Even that would add something like 30 gigawatts of extra generating capacity when they were all running together. And that's comparing to something like 70 gigawatts of generating capacity that will be running in the winter. So we've got a very substantial increase in generating capacity required. And that's not talking about any grid reinforcement. And just as a comparison, there's been a much more thorough study, it was done in 2019 by these people. They estimated 47 gigawatts for all the gas boilers in the UK. So I'm comfortable with my 30 gigawatts for half. So, in summary, I would say that many UK homes are heat pump ready, or can be made so by practical energy efficiency improvements, and that would give us an instant decarbonisation. If you did just the energy efficiency improvements, say halving the heat loss, then that reduces primary energy consumption by about 50%. Using the heat pumps, and remember that you put a kilowatt in and you get 3 kilowatts out, or for an air source, or better for a ground source. So that means that we will reduce the primary energy for heating our homes down to only 18% of what we use now. But that will still use a lot more electricity, so we will still use some more electricity generation. And it is actually going to be a huge infrastructure improvement task. And I remember as a teenager watching North Sea gas being retrofitted, or the burners being retrofitted to boilers and cookers in the homes of the UK, and it was a monumental task. It took weeks and weeks and weeks. That's the sort of scale of task we're talking about here. But of course, if the price of gas continues to rise, it will become, I believe, the most economically viable choice. And then, before we move on to questions, I just want to leave you with another quote from something This was a book written in the 70s around the 1970s oil crises. And as it says here, if you really want an authoritative long-range forecast, then listen to the oil companies, since they have the power to make their choice come true. Well, I guess my question is, do they want us to use heat pumps? Thank you. That's the end of the talk. I welcome some questions.
Thank you very much, Tony. We already have quite a few questions in the chat box. If you do have a question, can you please put it in? But I will read out the questions and ask Tony for a response. There are quite a few, so possibly fairly short responses. There's been no mention of heat store options using overnight low carbon electricity, e.g. caldera and warmstone.
That is true. It is simply going to be down to the total quantity of kilowatt hours you can store in those systems, and the physical size of them as a result. A bit like the hot water tank, if we're asking people to fit large volume and potentially large mass devices in their homes, then there are going to be barriers. Having said that, there may well be some roles for those sort of systems, and as you say, if they're heated from overnight low carbon electricity, then great. Yeah.
Okay. Don't heat pumps struggle on very cold days? How about a small top-up gas boiler or electric heater?
Ground source heat pumps don't, because they use the temperature way down under the soil. I mean, there are two types. There's often called slinkies, but pipes laid about a meter under the soil. The temperature under the soil sits at somewhere around 10, and okay, the heat pump will extract some heat, but it won't go down to -5 overnight. If you've got a borehole system, it goes way down. So ground source heat pumps don't do that. So they're excellent all year round. Air source heat pumps, yes, they do reduce their efficiency slightly as you get down to those temperatures, but the systems that are on sale, certainly around Europe, are designed to cope with that. And there's another measure of their efficiency, which is called the seasonal performance factor, and those are still quite good, certainly for the UK.
Okay, what is the environmental impact of manufacturing the new structural materials? So I guess this is about the embedded carbon,
yeah,
compared with the saving from operation.
I haven't done that calculation for a new build, but I have recently worked for a large landlord in London. In fact, we've just been commissioned to do the next phase of work, and there we're looking at converting and upgrading early Victorian apartments to what is it in London is London's net zero, and they asked this exact question. Well, you know, what's the carbon payback of doing this? And we worked out that for the first bit of the study we've done, which is a small 2-bedroom apartment, that the payback was within about 2 to 3 years. So that's an existing building upgraded. I'm afraid, as I say, I haven't done the new builds, but I imagine it's going to be similar.
I think this is a comment. Recent years, Oxford University's new accommodation have been built using prefabricated cross-laminated timber panels.
Yeah, that sounds almost like they're SIPs. So yeah, people out there using it.
Yeah, okay. Then the next question is, given about 75% of UK housing was built before 1980, what can be done to make insulating such houses technically and financially viable, such that heat pumps become viable? If not a heat pump, what heating option is viable for the majority of UK houses which are poorly insulated?
Yeah, it's a good question, and in fact, there was a bit of a joke in this sector a while ago that there is no such thing as a new building. Once they're built, they're all existing houses, and that's the problem. Yes, it's a challenge. Technically, it's definitely feasible, and I have worked on a number of buildings like that. It's a question of just getting stuck in and adding internal or external wall insulation, floor insulation, and roof insulation. For modest size houses, when that is done, then you can use a heat pump. And in fact, again, I think 3 years ago, we we did a study for an outfit, I think called Place First, up in Manchester, and they are they take on whole streets of old Victorian houses in the northeast and the northwest, and they strip them out, they refurbish them, and then they relet them as good quality low energy houses. So it is possible. The economics of that were working okay for them 2-3 years ago. That was on the basis that they were buying the whole street of houses for next to nothing. If an individual is trying to do it, of course, that's where we get that great list of barriers. But yeah, technically it's possible. I don't know the answer to how we encourage and or support everybody in doing that, I'm afraid.
Okay. Why heat the whole house when you could put the thermostat in the living area and close the door?
Absolutely. Zoning, quite agree. My house is zoned. Thermostatic radiator valves are supposed to do that to some degree, but what we need there is a behaviour change program to encourage people to do the right thing. But of course, a modern nuclear family where both teenagers are on their mobile phones, on Facebook or Instagram or whatever, in their own bedrooms and all the rest of it, it's a bit of a difficult one to persuade them to change, maybe.
Okay, but I don't understand the next question, and you may. It says TRVs ?
Thermostatic radiator valves, I think.
Ah,
yeah. I've sort of just indicated, I think, yes, good idea. If they're used properly. The latest generation, like so much else, are internet connected, and many of them you can control from your smartphone or laptop or whatever, or set up an automatic scheduling for individual rooms. So yes, I would certainly recommend looking into those for a short-term decent reduction in energy consumption.
Okay. There is a trend for people to move into cities and flats are less suitable for heat pumps. So what are the options?
Depends on the flat, really. A modern new build will be, generally speaking, to such a good level of insulation that it'll need very little heating. I mentioned the Victorian apartments that we're working on. Most of those, they don't quite have district heating, but they have a central boiler room feeding the whole block, or the whole what do I call it, stairwell, if you like. So there might be 5 apartments off the one stairwell. In that case, a large heat pump connected to that stairwell may well be the answer. But individually, I recognise it. Yeah, it's quite difficult.
Okay, comment. The Caldera system heat store stores 100 kilowatts, enough for a 4-bedroomed house.
Is that 100 kilowatt hours? Just to.
Sorry, 100 kilowatt hours. Yes.
Yeah,
Yes.
Yeah, so that would, for a modest, well-insulated 4-bedroom house, that would be a good day's worth of heating. Yeah. I mean, what's the physical size?
No doubt somebody will put it in, the person will put it into the chat. So I'll go on to the next question. What standards or methodologies are there that can be referred to when targeting the right air tightness during construction that complies with building regulations or passive house standards? Achieving the correct air tightness just before completion can be challenging, and I think you mentioned that.
Yes. The main standard that is used is the Passive House Certification Standard, and I know that unfortunately is quite an expensive route. It can cost 30,000 to just have the certification process. But in going through that process, a skilled and experienced assessor works from the design stage to check that the design has all included thought and detail for air tightness. And then at each construction stage, it's inspected and so on and so on. It is difficult, but a number of companies are becoming skilled at doing that. Essentially, in my experience, there's one company I do work with which does this a lot. What it comes down to is attention to detail. Firstly, certainly at the design stage, so the architects must, for example, we talk about they should put an air tightness layer, we would call it. That's not necessarily a physical component, but when they draw the drawings, they should say, where is this air tightness going to be delivered? If it's timber frame, it's relatively straightforward because it is actually a plastic layer. If it's brick and block, then where is it going to be? Is it at the inside of the internal blockwork, or where is it? How are you going to achieve it? And then as the building is constructed, it requires the site manager and the tradesmen to just keep their eyes open for filling holes as they go along. Then the technique is to get a skilled air tightness sort of measurement company. Normally they are there to certify, but if you get the right ones, you can bring them in at the early stage. You don't ask them to certificate the building. What you say is, right, do the test, what's the number, and then help me by going around the building, show me where the holes are, and we'll block them up, and then come back later when the actual certificate is needed.
Okay, I'll take one out of order because we have come back with the information. I've lost it. The Candeldra heat store is 70 centimeters diameter, 1.8 meters high, and weighs about 1.5 tons. So installed in a garage or outbuilding,
or on the ground floor in a new build. That's not completely out of.
Our informant makes it clear that he's not a representative of the company.
Okay, well that's even more encouraging. Yeah, that's not an unfeasible system for a modest, well-insulated house.
Yeah. How does the cost of a passive house compare to a typical construction?
If it's off-site construction, modular, and for example, to those registered social landlord specifications, then it's slightly more expensive. But and by slightly, I guess that's about 5 to 10% more expensive. But the running costs, including maintenance, are substantially less. If you don't have a dedicated heating system, you don't need your boiler serviced every year. You don't have to worry about topping up the water pressure. You won't get a radiator leak and so on and so on. If it's a new build, at the moment, all the new builds I've worked on are sort of self-built projects for individuals or their families. So it's difficult to extract the additional cost of the passive house from the unusual specific architect design nature of the building. What I will say though is that one simple calculation you can do is, well, if you were going to install, certainly if you're going for a heat pump, you might be spending, say, 15 to 20,000. Also, if you were, that's just the heat pump itself. But obviously, gas boilers only maybe 3 or 4. The whole heating system, I've seen quotes for a sort of biggish 4-bedroom house. The whole central heating system on gas was 30,000 installed. So you can buy a lot of insulation for £30,000. Is my response to that one.
Okay. Do you think that carbon neutral target for 2050 is realistic if new houses are still built with gas boilers and many old houses are not suited for heat pumps at the moment?
It's probably a stretch, I would say. Yeah, difficult one.
Okay.
Yeah.
No mention of solar panels. Is an electric heating system based on solar panels viable?
The problem with solar is that you only get about 2% of the annual output in the 2 months you want your most of your heating, which is December, January sort of time. So that's the problem. It's a mismatch between the seasons.
Just a comment, there are plenty of even major nationwide cowboys selling heat pumps. I have successfully fitted a heat pump system to a Victorian house, but many firms specifically excluded the essential radiator upgrades and ignored the need for any improvements to insulation.
Yeah, I agree. Yeah. It's in the barriers. Yeah,
it is a problem. What is a realistic target for percentage of homes that are new build or otherwise highly insulated by 2050?
2050. So what are we now? 2022. So we've got it all depends on motivation. If we think back to, as I say, when North Sea gas came in, we converted the whole country from town gas to North Sea gas in a matter of a few years, because as a country we were motivated to do so, and it was the state-run system that did it. If we look at the rate at which we've moved from coal and gas and nuclear-fired generation to the very high proportion of wind power and large portion of solar that we've now got, and some hydro, again it was down to the right motivation. So I don't think very much at all will happen without some sort of government incentives, policies, potentially subsidies. We need a clear direction of travel from them. Even thinking about London again with their net zero target, that's only 10 years away. At the moment, the large landlord that we're working for, it isn't clear what net zero means yet for existing buildings. No one has written the sort of specification sheet, the checklist. And without that sort of clarity, people aren't going to start to move forward. So yeah, with the right motivations, I think half of houses could be done, but with none, it may only be a few percent, because it'll be down to individuals who are motivated to do it themselves.
Okay, thank you. Sorry, I'm just 9-month and 11 months typical season access holiday let caravans. Typically, a lot of them, even built up to 2012, 13, still have single glazing, tend to be on the windy coast. A lot are electric panel heated or gas. Would air source heat pumps be practical, considering the difficulty of improving insulation?
Probably not. Probably not.
No.
Yeah.
Okay.
Yeah.
Do you think it will be industry rather that helps us achieve net zero, rather than simply having a government policy?
It's down to the incentives given to the industry. So if we again look at the renewable sector, the renewable sector, firstly there was something called the New and Renewable Energy Program back in the started I think in the late 70s, but certainly was running in the 80s and 90s. That was supporting the technology development. Then we had the non-fossil fuel obligation just after privatization of the electricity industry, which encouraged various renewables. It gave them a sort of a playground, if you like, a protected small marketplace that they could prove their worth. Followed by that, we had renewable obligation certificates, and then we had the feed-in tariff. So from, what was that, from about 1990 all the way through to about 2014 or 15, I think it was. So what's that, roughly 25 years of support. Now renewables are standing on their own 2 feet, then they don't have subsidy. So if we had a similar sort of environment for people developing and installing these technologies, then I think industry would just do it. Yeah. But at the moment, it's really difficult to know how much this cost increase in energy is going to incentivize the right people to do the right things, the right industries, the right companies to do the right things, because the right package of insulation and a heat pump and so on, as a retrofit, that there might be a way of doing that just using commercial finance and commercial companies, but no one seems to have come forward yet.
Okay, with one's own supply of wood, what about wood burning stoves for a partial or occasional use?
Yeah, good idea. And actually, as a secondary heating system compared to a heat pump, I should say that one of the great things about a gas boiler is that its efficiency doesn't really vary depending on sort of how you use it. You can up to a point, so it can run continuously, or you can run it stop-start, and it'll still retain its efficiency. A heat pump likes to work pretty much constantly, running gently in the background. That's not to say you need to run it 24 hours a day, but it does mean that if you want the building room warm at 7, you might need to start it running at 5. So it's better to slightly undersize them for efficiency, that means, of course, in the very cold snap, the beast from the east, then you're in trouble. So yeah, a wood burning stove in those circumstances would be a perfect partner for a heat pump.
Okay, thank you very much. I have put the links to our next Thames-Way meeting and also to the great debate, which is very relevant to the topic of tonight's talk in there. There are no other questions come up, but there is a comment which says, excellent presentation, thank you. And I would echo that. Thank you very much, Tony. It really has been an interesting talk. Well, thank you. Normally I'd ask for a round of applause, but I won't do that tonight. Yep, getting many more comments of thanks.
Well, that's great. It's a real pleasure. Real pleasure.
I will turn off the recording.